Okay, so one of our last looks at the calendar. Today's Wednesday. The conic sections we will continue talking about. We did a day on circles. We spent a day outside drawing a few different things. Today we will give a more algebraic treatment to ellipses and hyperbolas. Next class is our last class of new material. That's on parabolas and just kind of an overview of who cares about all of these shapes that we've been drawing. And then also our last quiz is on Friday. So that quiz is on just 2 days of stuff, circles and completing the square and what we do today. And then Monday is our review day, and then finally our exam is a week from Friday, 10:30, but probably I'll make that 10 o'clock. Any questions on the calendar at the moment? Okay, and don't forget the project is due by the last exam. Somebody's already handed it in to me. They got 100, so turn it in if you want to get this thing out of the way. To get 100, you just need to write thoughtfully. That's all. You don't need to write things that are positive or negative. You just need to be reflective, okay? The other thing I'll say about that last project is that, again, I want you to be honest and reflective, and I don't want you to worry about saying something that you think I want to hear or avoiding saying something you think I don't want to hear. I'm not going to read your projects until after I've assigned you a grade. I can tell you that the project that I've already seen got 100 because there was enough writing on it. So really, I'm not looking at content at the moment. I just want you to write a lot of stuff. Don't worry about saying things that are positive in the hopes that I will bump your grade up or avoid negatives for fear of getting your grade bumped down. Just write a lot of stuff. Reflect. And I'll give you 100. If it turns out you wrote like song lyrics on there just for the purposes of getting 100, I will go back and change your grade. But at the outset, you can write whatever you want. I'm not going to look at it until after I've got all the final grades submitted. Okay, on page 52, we spent a day talking about circles. Today we'll start with ellipses. Can we go to Steve for number 1? Do you guys remember the equations for the circle? It was x equals and y equals. Anybody remember what the equation was for the circle? Yeah, we had a cosine, we had a sine. So I'll put the cosine t and I'll put the, Todd, what is it? H plus r cosine t, and then, okay, so we had those equations. What's the difference? Different amplitude, yeah, that's a good way to think of it. In terms of the letters, what's different? Yeah, we've got r's. I don't care what the letter is, but they're the same number for a circle, right? The number in front of sine and cosine is the same for a circle. It's called r for the radius, but for an ellipse, it is not necessarily the same number. We call it a and b because they could be different numbers. One little note, you are perfectly welcome to swap the sine and cosine. You'll get a different ellipse, but it'll be an ellipse. I say different, it'll be drawn differently. It'll be the same, it'll look the same after it's drawn, but you're welcome to swap those. Let's try number 2. We'll go to Emily. Okay, so I'm going to ask us to make a table similar to the way we've drawn these things before. And the table will have t and then x and y. And we're just going to plot 4 points. We'll have like a left and a right and a top and a bottom, and then we'll connect the dots and make our ellipse. But once we've done that, then maybe we'll be able to figure out, well, there's actually an easy way to draw this ellipse without filling in the table. There's an easy way to find the left and right points right now and the top and bottom. We just have to know how to get it. But let's at least fill in the table at the outset. Can you guys split this up in your groups? I'm looking for 5 points. Well, actually just 4 because 2 pi gets you right back to 0. So can you divvy that up, find the x and y for these different ones? Okay, so we plug in the 4 special numbers there, and we'll plot these points. And then we connect the dots and we have our ellipse. And then we can talk about the shortcuts, like how could we have done this without like literally plugging points in? Well, can you figure out what the center is just by looking at the picture? What does it look like the center is? Looks like 2, -1. Is there something in the equations that would have told you 2, -1? Yeah, so there's your H and there's your K, and the center is HK. That's the same notation we used for circles. So the center is 2, -1. Next question. From the center, how far do we go to the right? 3. How far do we go to the left? 3. Is there something in the equation that said go left and right 3? There's all right, that's the only 3 that I see right there. Why does it say go left and right 3? Well, first, it's in the x. That's a left-right. Second, cosine normally goes between what numbers? 1 and -1. Multiply cosine by 3, and now it goes between +3 and -3. So it just says take your center point, which is at 2, go to +3 from there, go to -3 from there, and that's it. So this just says go 3 left and right from the center. From the center, how far was it to the top? That was 4, and to the bottom was also 4. And you can see a single 4 sitting in this equation, same place as the 3 was in the other equation. So this says go up and down 4. So the way that I think about ellipses is plot the center point, and then go left and right the correct amount, go up and down the correct amount. Just read them off the equation. You don't need to graph. You don't need to plot points like we did before with the table. Just go left, right, go up, down. I think it makes sense. Todd. The word center, I know we have the word center for a circle. The ellipse has a center as well. It's that point. That's the right word. The ellipse also has a couple of other points inside of it. What are they called? The foci or the foci. So that's not that one. But I think it's okay to call it the center. Nowhere in here do I see the foci. Turns out there's formulas for it. I think we'll see them, but you can plot it without having any idea about where the two foci were. Can we also look at this one? Was this one wider or taller? This one was taller because it was up 4 instead of wide 3. So just looking at those numbers, I think right away you can know, am I going to be a tall, skinny one, or am I going to be wide and short, just by comparing the 3 and the 4, the numbers in front of sine and cosine. Okay, so that's good. What if instead of 3 and 4, it was 3 and 3? Well, now it's a circle. Does our left, right, up, down business still make sense? Does it make sense that it would give you a circle? Yeah, if it's 3 and 3, then you go left and right 3, and you go up and down 3. And of course, that's going to give you a circle. So a circle is just a special case. Everything in the ellipse was, still applies to the circle. It just happens that they're the same left, right number as up, down number. Okay, so first some vocabulary. We'll go to Sam. Okay, the A and B, I've already forgotten where they were, so let's go back up. So here are our equations. A is the number in the X guy, and B is the number in the Y guy. And so 2A was called the horizontal axis. Does that make sense? How much was A in this case? It was 3. 2 times that number is 6. The length of the horizontal purple line there is how much? It's 6. So just 2A, it's not a formula you need to memorize. It's just, of course, 2 times A is going to give you the horizontal, and 2 times b, how much is that number here? That's, so 2 times 4 is 8, so that's the vertical. And then which one is the longer one is called the major axis. So in this case, the major axis is that vertical axis, longer in this case. When we're ready, we go to the next page. Todd? Pi times a times b. Let's find the area of the ellipse that we just saw before. Pi times, how much was a? 3. How much was b? 4. What's the area of the ellipse you just drew? 12 pi.
Oh, right. So like a circle, it's pi times r, which is the same.
You see it? You guys know the formula for the area of a circle is pi r squared. If it was a circle, we didn't use a and b. What did we use? We used r and r for both of them. And so pi times ab becomes pi times r times r. So that pi ab should replace. Forget pi r squared. You can delete it from your memory. Just know that the area of an ellipse is pi times a times b. And you get pi r squared for free. Okay, let's go to number 6, task today. Okay, so first let me remind you of the standard form we had for a circle. It was x minus h squared plus y minus k squared equals r squared. That was our equation of the circle. So because the ellipse generalizes the circle, I'm expecting an equation that looks quite similar to that. It'll have a's and b's in it. It won't have an r, but let's see what it looks like. So what we're going to do is the same thing we do every time we see sines and cosines, is try to isolate them. I know that sine squared plus cosine squared is always 1. So let's see if we can't isolate cosine in the first equation. What do I do? Move the h or the a first? So we'll subtract h, and then how do I move the a? Divide by a. So what I have is that cosine of t is x minus h over a. The other day we wrote that same equation for a circle. There was an r on the bottom. This equation, sine of t equals, okay, so we got y minus k over b. For the circle, we wrote that equation, but it was not a b, it was an r. And then I'd like to do what to both sides of the equation here? Square them, and then add them. We're just trying to build sine squared plus cosine squared. So I'll go ahead and square this guy, and square both sides of the other. And so that means that if I add these equations, I get x minus h over a squared plus y minus k over b squared. Then what do we get? Well, we get cosine squared plus sine squared. But how much is that? It's 1. So that's my equation. And that's not how most folks write it, so I'll just write it the way that you'll see it in the book. It just squares the top and bottom separately. So it becomes x minus h squared over a squared, just bringing that square in. Okay, that's the standard form for an ellipse. It looks quite similar to the standard form of a circle. In fact, if I wanted to, see, for most of our equations, there's going to be a 1 sitting over here. If I don't want r squared here, but I want that to be a 1, what can I do to both sides? Yeah, let's divide by r squared. So that would become a 1. Each of these guys would have an r squared on the bottom. And now it's exactly the ellipse, but two different numbers on the bottom instead of r and r.
So they would never want you to get a squared, b squared.
No, because you can't, well, if you choose to put the a squared and b squared over here, that means that there's going to be some numbers sitting in the front there, and we choose to not put any numbers there. It's kind of nice to have a squared and b squared on the bottom because, again, a tells you how far you have to go left and right. It's the same a. So if it's written this way, then right away you can pick off how far do I go this way and how far do I go up and down because that's the b. Let's try 7 with Kate. Okay. The other day we had equations of circles that looked like that. I think we called it useless form, and we tried to get it into standard form. So what was the main technique for the circles? Was completing the square. So let's see if we can remember how to do that. So first step was to kind of group together the x's and then leave some space and then group the y's. And we'll go ahead and move that negative 23 over. At this point, am I ready to add the magic number to both sides? No. Topher had asked the question the other day, what do you do if it's not just 1x squared? What do we do if it's 4x squared? We got to factor out that 4. Our magic formula just doesn't work unless it's a 1. So let's pull that 4 outside. What do I factor from the y's? 9. Let's factor out the 9. Okay, then we need to find the magic number to add in the parentheses. Remember the technique was you take b, which is the guy touching x, you cut it in half, and you square it. What do I get when I do all that? I get 1. So we're going to put a plus 1 right there. Take b, cut it in half, square it. All right, I don't like going around randomly adding 1 to one side of the equation without balancing the scale. So should I add 1 to the other side? It's a 4, right? It's not a 1. That 1 is not really a 1, it's really a 4. Okay, then we had this question about is it an add 4 or is it a subtract 4? Depends on where you put it. I added 4 on the left side. If I want to balance the scales, I add 4 on the right side. The way that we did completing the square initially, we didn't have a right side. We just had an expression. We didn't have an equation. So I couldn't add 4 to something that didn't exist over there. The opposite of adding 4 right next to it is subtracting 4. So if you just get it straight in your mind, whether you add or subtract, doesn't matter to me. You just got to do the right thing depending on where you put it. If you choose to subtract 4, how do you move it to the other side? You add 4. That's the same thing that we're saying. So just be consistent. Find some way that works for you. So we'll go ahead and put this back. So it's a 23, and then we need to add 4 right there. And same magic formula. You take this guy, you cut it in half, and you square it. What do you get? You get plus 1. What do I need to add to the other side? We add 9 over here. Okay, next step is to write this guy as a perfect square, and then write the other guy as a perfect square. Over here we have a 36. What goes in the first parentheses? X plus 1. That's factored. Second parentheses, y minus 1. Okay, this one's almost done. I'll point out, again, a feature of the standard equation. It's highlighted there in the green. You need it to equal 1. Quadratic equations, you make it equal 0. That's the magic number for quadratics. For ellipses, you make it equal 1. That's the standard form equation. So what should I do? Let's see, I have a 36. What should I do to both sides? Divide by 36. Don't divide by 4 because you want to get rid of the 4. I don't care about the 4. I care about getting a 1 over there. Don't divide by 9. Divide by the number that's sitting over here. So we divide everything by 36. And then I think we'll have our equation. So what is it? X plus 1 squared over, what happens when I cancel? 9. Y minus 1 squared over 4 equals 1. That's the goal. And now that it's written that way, I'd like you guys to write down a few things. Write down the center of the ellipse. Write down the left-right distance you have to go from the center to get to the extreme points. And write down the up-down distance you need to go from the center. Okay, what is the center of this ellipse? So it's negative, whoops, I always forget that. It says negative 1, 1. Don't forget to change the signs inside of those parentheses. Negative 1, 1. And then the left-right distance is what we were calling A. And the A is the thing under the bottom, under the X's, but that's not A, that's A squared, right? The equation is an A squared. So how much is A? It's 3. So if you have your center point, you go left and right 3. That will get you your extremes on the right and left. Up and down is 2 because that's B squared over there. B squared is 4. So B is 2. Go up, down 2. Is this one taller or wider? It's wider because we went 3 versus only 2 up, down. Todd? The total distance between the top and the bottom is a 2b. And the total distance between left and right is 2a. But I'm just saying from the center, how far do you go? Yeah. Okay, so while you guys are doing that, I went over here and opened GeoGebra and I just typed in, not the standard form equation that we did all the completing the square to get, but the original. Again, we said the center was going to be, what was it? Negative 1, 1. And then we said left and right 3, up and down 2. We hit enter. Center point, we said negative 1, 1. That's right there. That looks pretty good. How far left and right? You can count, yeah, from that. Well, in fact, it's easier if I just put the dot. So we said the center was what? Negative 1, 1. So from there, it's a 3 left and right. How far up and down from there is 2. How long is the major axis? It's 6. How long is the minor axis? 4. That's the 2A and the 2B. Questions on any of that? It's interesting to me that, remember we did this the other day and I typed it in for a circle and it didn't write over here. It didn't write down what I typed. It did the completing the square version of the circle, but it didn't do that for the ellipse. Interesting. Okay, that's fine. Number 8, Richard. Okay, so that's what we're looking for. I'm trying to give you more general equations of these conics, like when is it a circle, when is it an ellipse. We'll see a hyperbola in a moment, but if A and C have the same sign and are both not 0, how much was capital A in our equation? It was 4, right? Capital A is the thing in front of x squared. How much was C? C was 9, both positive. Neither one of them 0, sorry, both the same sign, neither one of them 0, that makes it an ellipse, which means you can change those numbers, but as long as you make, as long as you keep those two things same sign and not 0, then it's an ellipse. So for example, I could come over here and I could change. Instead of 8x, I could make it 20x. Well, A and C are the same, right? 4 and 9. It's still going to be an ellipse because they're still same sign and still not 0. You can take a look. I'll hit enter and that ellipse will shift. There it is. Got a little bit bigger, moved a little bit left. Great. If I make this guy, instead of minus 18, we'll make it minus 2. Still going to be an ellipse. It's going to shift. I can change to 23. Instead of 23, let's make it 53. Okay. Kind of stayed where it was, but just got bigger. That seems reasonable. All right, what if we change the 9 here? Let's change that 9 to a 16. Is it still an ellipse? Yeah, because it's the same sign. It's now 4 and 16, neither one 0. It went like that. That's interesting. Let me put that back. What didn't change when I did that? Yeah, like the width is still the same. The left right is still the same. What was the old height here? The old up down from the center? Is that the old one or the new one? I lost track. Where's my center now? Is it, oopsies. Is it easy to see the center? Is it here-ish? I guess it's not as clean. Looks like it's about 3. All right, and then if we change it to that. All right, I've lost track of the undos and the redos. But you can see that changing these things has various effects on the ellipse. What if I make this a minus 9? Is it still an ellipse? We said that to be an ellipse, those two things need to be the same sign. Is this going to be an ellipse? No. I don't know what it's going to be, but it's not an ellipse. It's got to be something dramatically different. Somehow making it a negative 9 instead of a plus 9 changed it drastically. Went from that to that. Okay, what if I change this guy negative 7? Now they're both the same sign. Well, where'd it go? I don't know where it went. There it is. So still an ellipse. There's other conditions, obviously, but what you're looking for is A and C. The x squared and y squared terms need to have the same sign, not 0. If you make one of them 0, for example, a 0 there, is it an ellipse? No. All right, so we got 1 vote for line. Any other votes? Second vote for line. All right, so it's off the screen. No problem. So just changing the signs and making 1 0 like really changes what the thing looks like. So that's all that question is about. Let's try. Okay, so we actually kind of did one right here where A and C had opposite signs. That was the hyperbola. We haven't really talked about those, but let's go ahead and move on to 10. Chris? Okay, if for a moment I decided to call this cosine and this sine, now what graph am I going to be looking at? That's an ellipse. That's what we just studied. But if you change the cosine and sine to secant and tangent, you get a drastically different thing. It is called a hyperbola. We'll look at some right now. And you can swap them. It doesn't matter which one goes first, but it's the same equations. H and K still mean the center. A and B are still going to mean left, right, and up, down distances from the center. Topher. If we did cosecant and cotangent. Wait, say it again? Yeah, I don't know what that would be. Secant and cosecant. I have never thought about graphing such a thing. All right, so if we pulled this on the calculator real quick, any thoughts? Mode, parametric. Okay, so we're doing, what did you say, secant and cosecant, right? So I'll do like 5 plus, okay, so I can't type, 2, I can't type in secant. I have to divide by what? Divide by cosine. Okay, so that's fine. And then I'll do something like a 3 plus 6. And then you said cosecant, so that's divided by sine. A flower. All right, let's take a look. All right. Let's go a little bit higher. There was something happening up at the top there. Okay, so this is not a hyperbola. Hyperbolas have 2 pieces. This thing looks like it has 4. You want this? Yeah. But there's big spaces in the middle, right? There's like this whole horizontal band, which is outlawed, and it's at 1. Yeah. Yeah, the circle would fit quite nicely in the middle there. Yeah. All right, that's a topher. Okay, so if we were to eliminate the parameter, let's not go through the same thing. It's analogous to what we did. Where did we do it? At the top here. Remember we had to solve for cosine and then square both and add them and use cosine squared plus sine squared as 1. Okay, so you do the same thing. It turns out to be almost identical to this equation here in green. The only thing that changes is there's a minus sign where there was a plus sign. I'm just going to write that as the answer. You can follow it. The goal for this guy is to use the identity that tan squared plus 1 is secant squared. We saw it. We didn't use this one near as often as the sine squared plus cosine squared. But if you use that, then you'll get something like x minus h squared over a squared minus y minus k squared over b squared equals 1. And here it actually does matter the order in which you write them, so I'll put the same thing, but just make the other one negative. Those are different. We always make it equal 1, so do what you need to do on the left to make it equal 1 on the right. We'll see an example where we actually do it. But here are our 2 versions. They are slightly different graphs. Well, slightly, they're completely different graphs, but they have a lot in common. So depending on which one is positive and which one is negative, will tell you something. We'll get there as we do an example. And the way to know which one is which is to know which one is secant and which one is tangent. Let's see if we could think about this one for a second. Get rid of the topher. Let's see. So at the moment, I have y has the tangent in it. So that means that right here where I see this tangent squared, it's going to have something with the y in it. It's going to be this term right here with the y in it. I don't know which one, but I'll have a y in it. And then I'll have a plus 1. And then I'll have a secant squared. So basically my equation is going to look like something with y plus 1 equals something with x, according to the equations that we have here. If I wanted to solve this one and make sure it's a 1, I always want it equal to 1, then what happens? I get move the y over by subtracting it. And this is the x minus y version equals 1. So the equation that I wrote up here, where x has the secant and y has the tangent, is the x minus y version. It's that one. The one on the right would be fine if we just swapped the tangent and the secant. You get the one on the right. I don't have that memorized. So let me give you a problem that I actually might ask you to do, say on the quiz on Friday or on the final exam. So on the next page, number 12, we'll go to Kyle. Kyle? Okay, so let's give this one a shot. So we've got our equations right there. The goal again is to write it in standard form. In fact, forget standard form. We'll just jump to the punchline here. We're just going to draw. What do you think the center of this hyperbola is? Do you remember where to find the numbers in this form? It's 2 and 4. You don't change the signs here. You just read off 2 and 4 as they are. So we'll go ahead and plot the point 2,4. Okay, let's see if we can figure out how far we're going left and right. In those equations, one of the numbers tells you how far left and right. It has to be in the x, and it's not the 2 because the 2 is the center number, it's the 3. So we're going to go left, right, 3. Left, right, we're still going to call it A, it's 3. So then what we're going to do is find 2 more points. Go right 3 and go left 3 from your center. Okay, same kind of game with the up-down. How far up and down is it? It's 2. It's the 2 in front of the y trig function. We'll still call that B. So see if you can plot 2 more points. You're going up and down 2 from the center. All right, any questions so far on those 4 points? If I connected those 4 points like we did before, what shape would I draw? An ellipse. Okay, let's go ahead and draw the ellipse. The ellipse isn't really going to help us with drawing the hyperbola in a second, but I can make very small changes to those equations and get that ellipse. What would I change? Secant and tangent would become sine and cosine in any order, and we get that ellipse. Okay, so it's not that ellipse, but that's okay. Instead, what I want to do is I want to draw a rectangle. I want to draw a rectangle that hits those 4 points. So draw that rectangle. And the whole point of the rectangle is to draw the diagonals of the rectangle. Turns out the diagonals of the rectangle are going to help us find the actual shape of this ellipse. So draw the diagonals of the rectangle, but extend them. Let those diagonals go all the way through. And at this stage, we are just about done. I'm ready to draw my hyperbola. Hyperbolas have 2 different pieces that kind of go away from each other. We saw a picture of it the other day. All right, so the hyperbola looks like one of the following pairs of things. The hyperbola is going to hit these blue dots, and it's going to be completely outside the rectangle, and it's going to go towards those dotted lines. Those dotted lines are asymptotes. They're slant asymptotes. Normally our asymptotes are horizontal or vertical. These ones are tilted. So those are slant asymptotes. That's the one. Can you draw the other one on the left-hand side? It's got to hit your rectangle and run away. And it also has to get very close to those asymptotes. So that could be our hyperbola. But just as well, do you see that we could have drawn the hyperbola up and down? Okay, draw that one instead. Okay, and the last piece of this puzzle, let's figure out which one it is, because it's not both. The equations that we're given, it's either the purple graphs or the black graphs. We just have to figure out which one it is. I'm sure there's some easy way to just remember, oh, whichever one has secant tells you it's that one. But I don't remember what that way is. So let's analyze for just a moment. Take a look at plugging in, for example, t equals 0. Let's just plug in t equals 0 and see how much we remember. X is equal to 2 plus 3 secant of 0. Secant of 0 is not one of the ones that I just have memorized, but I do know that secant is 1 over cosine. Okay, now we're getting to something that's familiar to me. How much is cosine of 0? So that's 2 plus 3 over 1, which is 5. Of those 4 special points that we plotted, one of them has a 5 in it for the x. The hyperbola hits that point. If you checked, you could go ahead and find the y value. 4 plus 2 tangent of, what number are we plugging for t? 0. Tangent of 0 is 0. So this is 4. So the point that this, one of the points this hyperbola hits is definitely 5, 4. I'm sure there's an easy way to get around doing that, but I have enough stuff in my head. So I find one point that's on the hyperbola, and I grab that. Todd. Yeah, the asymptotes will always be those. Yeah. Okay, so then I think we win. I'll just highlight the ones that are in. So this and the other guy. Those ones are the hyperbola that we were supposed to graph. If we want to find the equations of the asymptotes, we can. I'll say that we won't do it right now, but in order to find the equation of a line, you need 2 things, a point and a slope. You could find the point, 2, 4. It's definitely on the lines. And then to find the slope, well, you have a rectangle here. You can find your rise and your run by just thinking about the rectangle. And then you can find the equations of both lines. If I wanted the hyperbola to be drawn as the purple ones, it's a real simple change to make to the equations. Just flop the secant and the tangent. Keep all the numbers just where they are, but make it 3 tangent of t and 2 secant of t. That will make it purple. Okay, and then the last thing I think we wanted was the standard form equation for this one. Let's give it a shot. We had 2 basic forms. You had an x minus y form equals 1, and you had a y minus x form equals 1. This green hyperbola that we were actually drawing here was the left-right one. The x was the dominant one. You have a guess as to which one is going to be the equation? Is the x minus y one. So x minus something squared over something else squared minus y minus something squared over something squared always equals 1. This is a left-right hyperbola, so the x is the positive one. The x dominates here. The numbers in the parentheses are the center points. What's the center? 2 and 4. Be careful about where you put them. Could you imagine if it was the other equation where the y was first? Imagine just swapping the x and the y terms. Do you just put 2 and 4? No, you got to put them where they go, right? X was 2, y was 4, divided by, okay, A is still the left-right number. A is still the number that's highlighted in green. A is what we called A. What goes down here is A squared. That's a 9. Underneath the other one is B squared. What's that? 4. Okay, and if I asked GeoGebra to graph this equation, the one that we just wrote with x's and y's, it would give us the left-right hyperbolas. The one that goes first, it depends on whether it's the left-right one or the up-down one. To figure out which one that is when I have a picture, I'm just going to plug in 1 point, and then I got 5, 4. Okay, that's over there, so it's the left-right. If it's left-right, the x is the positive one, and the y is the negative one. If it's up-down, swap them. Sam? Mm-hmm. That's exactly right. So Sam has got some theorem that, like I said, it's out there. I just don't remember it ever, so I have to do what I just did. But if the secant is with the x, it's going to be a left-right every time. If the tangent is with the x, it's going to be an up-down. It's really just a matter of which one has the secant, which one has the tangent. But I have too much stuff to memorize, so I'm happy to plot a point and get it that way. Okay, so I want to give you guys the last 20 minutes to draw some pictures, so I'm just going to come down here and show you at least briefly why we call these things the conic sections. We had circle, ellipse, hyperbola. Next class, we'll talk about the parabola. You guys know what a cone is. You go to the ice cream place, you get an ice cream cone. It looks like this if you're really lucky, but probably you only get like half a cone. So you should tell them you want the double cone, like twice as much ice cream. Don't get sprinkles on the bottom. It just falls right out. So here's our double cone. If you take the cone and you slice it, let's take a look at this. Where is this guy right here? If you slice the cone with a plane going right through the cone, what kind of a shape is there in yellow? That's a circle. Wonderful. That's if you happen to go like perfectly like perpendicular parallel, like you just get it right. But if your plane is at an angle, now what kind of a shape is traced out in yellow? That's an ellipse. If instead you happen to decide to make your plane go up down, well, now the plane hits the cone, the double cone, twice. What's that yellow shape? That's a hyperbola, and it doesn't have to be perfectly up and down. You can also make it slanted, and you'll still get 2 branches. It looks like one of them is bigger, like the one on the bottom looks like there's more. Well, if you extend the cone, they'll be exactly the same on both sides. So the last one is this parabola. The parabola is really a special one. The only way to get it so that that plane doesn't hit the parabola, it doesn't hit the cone again down here and give us an ellipse, and doesn't hit the cone at the top, which gives us 2 branches of the hyperbola, is if that plane comes in parallel to the angle, like the line of the cone. Like you can see the cone has this kind of a line. If you slice it exactly parallel to that line, you will get a parabola. It's got to be perfect. That one's really picky. What do you mean? Yes. Yeah, it is a straight line. It's the same straight line going behind the cone up at the top here. If you slice in parallel, you're going to hit this bottom cone only. Not going to hit the top one because you're parallel and you're off of the cone a little bit. If you make it steeper, then you will accidentally start hitting up here and you'll be back. If it's shallower, then this parabola doesn't just go on forever. It will eventually kind of loop back around and you will get a very long, skinny ellipse all down at the bottom. Yeah, you got to make it so it just barely hits this guy, but doesn't accidentally come out and hit the cone again.
And then you alter the shape by moving moving the cutting surface down or up along that.
Yeah. Yes, and you can sweep through and get all the different kinds of conic sections and different sizes and things like that. So that's why we call them the conic sections. You make them all from the double cone. Okay, lots of practice on the next page. See if you guys can work with each other. I think there's an answer key that follows, and I'll walk around.